Good afternoon. My name is Bart Iver van Blokland, and together with Professor Theo Harris, we have written the paper Partial 3D Object Retrieval using local QUICCI descriptors and Dissimilarity Tree indexing. Now let's start with the beginning, because what is partial 3D object retrieval? And in order to illustrate that, I have brought these teapots with me. Because when you are doing partial 3D object retrieval, one doesn't really have the entire object available that you're trying to look for. Basically, for example, when your 3D scanner is making a 3D picture of the scene here, it might not be able to see everything there is to see and therefore doesn't have as much information as any other retrieval method might have. One of the other problems is, and this can basically happen to anyone, is that accidents occur. In that case, one might only have a very small portion of the object and would like to find out where that part came from. So let's say we have just broken our favorite teapot and would like to find a replacement. What do we do? Well, we could use the method that we propose in our paper. This method consists of several major components. First of all, we need a partial shape. So in our case, that would be this fragment that remains from our accident. The second thing that we need is a set of every teapot ever made. That will be complete objects. In order to find which teapot this portion here belongs to, we first need to take a closer look at the surface itself and represent it in some way that allows us to find it in the set of complete objects. But doing this kind of point by point is really slow. So therefore, we need some kind of way of accelerating the retrieval of similar surface points. This we do through the proposed Dissimilarity Tree. Finally, we need to be able to determine which object is the best match for this particular surface, which we also present in the final part. So for starters, let's take a look at the modified QUICCI descriptor and why this is necessary. And we'll do that by taking a look at a teapot. However, since we're doing partial object retrieval, we need a query and a matching surface, so we'll be needing two of them. Now, unfortunately, as you can see, neither of these is damaged, and also not from this side, so let me go ahead and damage one of them. Except you can't really see that from this side, but now you can. Okay, so I've mentioned the QUICCI descriptor, but what is this? Well, the QUICCI descriptor is a descriptor that we proposed last year. And as you can see, the descriptor is shown in the bottom left here. If I turn the support volume on and off, you can see that the outlines of the handle of the teapot are visible in the descriptor. This is something that inherently happens as a result of the way it is constructed. Also, this descriptor is constructed by counting the number of intersections between the object surface and circles. This is relevant later. Okay, so let's take a look at our two teapots. Now when I move the support volume of the descriptor back and forth between the two teapots, as you can see on two corresponding points, it is producing the exact same descriptor. This is very desirable behavior. However, when we're now moving the support volume to a part of the teapot that is damaged, there's a lot of additional responses present there as a result of it only being a partial surface, and these are not present in the descriptor of the unmodified teapot. Now, this is exactly why we have proposed a modification to the QUICCI descriptor, because we want to find some way to filter these responses out. And in order to understand how we did that, we'll need to take a closer look at the object surface. Remember that we have used circles to generate these descriptors. And the real key observation here is that if you take a close look, there are the descriptors that are going through the object surface twice are part or interesting or typical to the surface, while those only intersecting once are not. So all that we do is that we filter out all of the responses that are only intersecting the object once. And the result of that is this. And if we now look at the corresponding point on the complete teapot, you can see that the descriptor is a complete subset. This we can really utilize well for partial retrieval. Now we also did a quantitative analysis of this, and we found that in the vast majority of cases less than 10% of those undesirable bits were remaining in the descriptor. So this filter is very effective. Okay, so that's the first major component done. Now we'll take a look at the second one, which is the dissimilarity tree. And before we get into the algorithm itself, we need to talk about how we compare these descriptors. But of course, they're binary descriptors. Why don't we use Hamming distance? Except when we try to find surface contours similar to those shown on the left, using regular Hamming distance you get really bad results. The top ones here are not that bad, but the later ones really are not. That is why we instead proposed the weighted Hamming distance function in last year's paper. As you can see, the top results here contain the exact surface contours we're looking for. Now the weighted Hamming distance function is essential to understanding the dissimilarity tree. When you compare binary images, each individual bit can have two types of errors. You can either have a false 0 or a false 1, which we will denote with a type 1 error or a type 2 error. In the case of Hamming distance, both of these errors have a weight of 1. You just count how often any such errors occur. But for weighted Hamming distance, you instead count each bit error by how often it can occur, as you can see in the equation here. As an example, in the case of our QUICCI images, there are a lot of zeros, but very few ones. Therefore, the type 1 errors result in much more distance than type 2 errors. So now back to our problem. We want to find images similar to the ones we are looking for. We've already established that we want to use the weighted Hamming distance for that, and third, we want to be able to find them quickly regardless of what the image contains. As it turns out, this is not easy. Let me show you why. Because weighted Hamming distance depends on the image you're trying to look for, you don't know how to structure your index in such a way that you can always find any match quickly. Or do you? Meet the dissimilarity tree. This is what it looks like. Now there's a lot to take in here, and don't worry too much about the images themselves. What you need to focus on is that it is a binary tree, and each time you go left, more dark areas appear. The tree works on the back of two main observations. First, let's return to the weighted Hamming distance function. Remember that a moment ago we said that for QUICCI images, generally type 1 errors are far more important than type 2. An effective index can rule out a bunch of descriptors at once. You can only do this when the distance to your query to all those descriptors is high. So, for efficient querying, you want high distance values to as many descriptors as possible, so you can discard them all at once. We do this by designing the tree in such a way that it maximizes the number of type 1 errors incurred when navigating the tree. The second observation is that descriptors are not distributed randomly. So here you see 36.5 million QUICCI descriptors laid out on top of each other in a heat map. And these are generated from the Strike 16 partial object retrieval dataset, which we use for evaluating our methods. So what we did was at each node to divide the index descriptors half on half between the two branches. The left branch contains descriptors which all have a region set to 0. The intermediate nodes in the tree show the OR operator applied on all images contained in that branch. Thus, when a pixel is black, all bits are set to 0 there. Whatever descriptors are left are stoned in the other branch, and the procedure is repeated for each of them. This process works because whenever a descriptor has a particular bit set to 1, having a region of zeros means you pretty much immediately incur a distance penalty. Is this effective? Yes, it is. Relative to a sequential search, using our dissimilarity tree is much faster. So now, if we have a descriptor from our query object, we can quickly find a potentially similar surface point in other objects. This brings us to the final part of our pipeline. We can find similar points to the ones in our surface, but we still need to determine which object is the best match for our query. How do we go about this? Well, we did an experiment for this. We took our query object and we took random points from its surface. Then, for each of these points, we determined which object the best match to that particular point belongs to in our dataset. Next, we charted how many votes each of these objects got over time. As you can see, there is clearly one object which is more often the nearest neighbor of these surface points than others. Therefore, what we can do is to sample random surface points and find the most similar points in our database, vote for whichever object it belongs to, and when an object has received a set number of votes, we deem it to be the best match. As you can see, under optimal conditions, the method is able to identify partial objects nearly perfectly. Under more realistic conditions, lower resolution QUICCI descriptors, which by the way are also much faster, perform quite decently. Also, as you can see, the vote threshold doesn't really matter much, and you can get away with a very low number of them. Its performance in one part of the Strike 16 partial object retrieval benchmark is also very favorable relative to other methods. And there you go. That's the final component of our method for finding partial 3D objects such as teapots. That's about it. Thank you for your attention.